Hi everyone, welcome back. We are, excuse me, we are picking up on the discussion in reverse mode versus forward mode automatic differentiation, and along the way developing intuitions for what will eventually become backprop. And as I'd mentioned, these couple of lectures last time, today, next time, these are one of the, I would say, some of the densest material in the class. We tend to just work through a lot of examples, do a lot of math on the slides. But this is not the norm for the class. It'll get better again. You've hopefully seen some of the earlier lectures where it was a lot more visual. We're talking about image classification, so there's a lot more pictures to see. We have to dive into the weeds at some point of time, and this is that time, but it won't always be like this. So hang in there. Okay, let's take a quick recap from last time. We have a number of things that we were covering. We were deep into the woods of computing gradients. We had already looked at how to do that numerically. We were in the middle of going through all the notation and techniques necessary, chain rule to understand analytic or manual differentiation. And this was all as a stepping stone towards building up towards automatic differentiation. And we will not cover symbolic differentiation in the class. And so the notation that we had introduced is that anytime you have a variable in the numerator, if you will, that corresponds to the first dimension or the rows. And so the gradients of vectors with respect to scalars are column vectors for us, and the gradients of scalars with respect to vectors are row vectors for us. That's the second dimension. And that's just the convention we follow. You should be aware that there's an opposite convention. And the most common object we will be interested in this class are the gradients of losses with respect to parameters, but we are going to be computing gradients with respect to intermediate activations and everything along the way, as you will see. We introduced this notation of a Jacobian. This is the most common object that you'll be dealing with in a computational flow graph and neural networks, because somewhere along the way, these are intermediate activations with respect to parameters or activations coming in from the previous layer. And so every layer in a computational flow graph will have a corresponding layer Jacobian. And it will have the size of output variables times input variables. We ran through a couple of examples where we went through, for example, if the layer in a neural network is a fully connected layer that just takes the incoming vector, does a matrix multiplication and gives you this is a fully connected layer, then we know the layer Jacobian is simply the matrix of weights, if you will. W matrix is the layer Jacobian. With respect to X, the activations. You also will need to compute the layer Jacobian with respect to parameters. We also talked about extension to tensors, where X and Y are, high dimensional objects. And this is in practice what we deal with the most. We do not actually simply deal with single vectors, but we said that, in order for the math and the analysis, it'll just be easiest if you think of them as long vectors. So just string up all elements of Y and X into a long vector, and then you can still think of this as the Jacobian matrix of such a layer, even though this shouldn't be a matrix if you think about this object gradient with this object. Because ultimately we have to start indexing every single element of Y and every single element of X. But if you start, just string everything up into a vector, then this layer is also corresponds to a Jacobian matrix. We had started getting into, the things that we will care about are cascaded functions or composite functions, where we will compute functions of the output computed by another function, and these are what layers in a neural network will correspond to. And we will ask for example, the gradients of the loss with respect to the first variable. Of course, there will be intermediate variables, which are W's or parameters, but, writing everything simply, we will be interested in such composite functions. We had gone through chain rule for a scalar, which was the simplest possible case of understanding this. If X is converted into Z, which is converted into Y, the partial of Y with respect to X is just scalar product of these two partial derivatives. And because of the way we had constructed our notation, we could just replace everything by arrows, and this object became a matrix multiplication. So the Jacobian of a composite function was just the product of Jacobians of the elementary of the ingredients that went into their composition. Okay. And so we had also done an intuitive understanding of this Jacobian. So we had said that, the Jacobian of y with respect to x, each element, I comma j element of this composite Jacobian matrix could be viewed as an inner product of this row with this column when we start multiplying the Jacobian matrices, and that essentially gave us summing over intermediate variables. We also looked at a graphical view of that same perspective, where we wrote down nodes in a graph which corresponded to coordinates or elements in this vector, and we asked if you want to know how much yi this node is affected in this graph by epsilon perturbations to xj, you have to reason about all paths from x to y. And those paths are essentially the intermediate variables, and we take the product of partials along those paths. And so this was just a graphical interpretation of that exact same concept. And of course, we don't have a composite of just G1 and G2 in the kinds of things that we'll be doing. There'll be an H0, H1, perturbed by G1, G2. There are a sequence of such functions, and of course, they can be constructed in arbitrary order. They're not just chain structured. But the sequence, the chain structured sequence, allows us to easily analyze the fact that the Jacobian matrices are getting multiplied, and that is giving us the Jacobian of the last activation HL with respect to H1. And what we had said was, if ultimately you're going to compute a scalar, we had noticed that vector matrix products are far more efficient than matrix-matrix products, which ultimately culminate in a matrix-vector product. And so the direction in which you multiply these matrices matters. It matters for computational efficiency. It does not matter for accuracy of the answer. You get the exact same answer, but your computational complexity will vary depending on the order in which you multiply these matrices. One order, the left to right order in this slide, corresponds to reverse mode automatic differentiation. The right to left order on this slide corresponds to forward mode automatic differentiation. And you will see that in a couple of slides. We will show you, we'll work through a scalar example where things will be simpler, and we'll show you that. The intuition that we had hoped to convey to you is that we will think of deep learning as differentiable programming, that we will express computation as a graph structured object, where the input to the computation is the data, x, y, and the parameters. So data being x, y, parameters being w of the various layers along the way. The output of this computation is just a loss computation. And scheduling is the same as topological ordering. How do I perform this computation? Well, I need a topological ordering on a directed acyclic graph. And that's why we had introduced the notion of a directed acyclic graph, that are directed graphs. So all edges are directed, and there are no directed cycles. So you cannot follow the directionality of edges to return to a vertex by following the directionality of edges. And we had said that directed acyclic graphs have a one-to-one correspondence, and you are actually showing that in the homework. You don't need any specific knowledge or skills to be able to show that. You just sit down and start from one direction. If I give you a topological ordering, can you construct a graph and prove that graph is directed acyclic? And if you start from a directed acyclic graph, just knowing the elementary properties of that, can you come up with an algorithm that shows to me how to compute the topological ordering? There's a lemma that you need about, there exists at least one vertex that does not have any incoming edges, and you'll be able to show one-to-one correspondence. The reason why that one-to-one correspondence is important is that topological orderings are the primary objects that we will care about. They allow us to do scheduling of computation, and following the topological ordering. So for example, the fact that there is x1, x2, x3 means that I can first do this computation, then this computation, then this computation. By the time I come to x4, nodes for us will correspond to computations. By the time I come to x4, I am guaranteed that the input to this computation has already is ready. It has been computed, that I don't have any dependencies that are yet unresolved. I will never have to wait if I follow the topological ordering in scheduling my jobs, if you will. You can view these as jobs. Okay, so this is the example that we were working through, that we had just begun, and that we're going to spend large parts of today working through. We were given a fairly simple function. By the way, if you'd like to work through this example yourself, or you'd like to see these written down, there is a note on the class webpage where we have linked to a tutorial that walks through exactly this example and a couple of others. So you have, my scribbles on these slides are for this live feedback, but yes, all of this is written down, so you can read a paper if you like more formal LaTeX style math for your reading. Okay, so we have a function f of x1 comma x2. It computes the sign of x1, which we will name an intermediate variable w1. It multiplies x1 with x2, which we will name an intermediate w2. And this is how we had constructed this computational flow graph. x1 and x2 were inputs. There is, the nodes correspond to computation, sign and product and summation. Data flows on edges. So x1, w1, w3, which is the sum, which is the same as f. And this is also x1, this is x2, this is w2. And this is an instantiation of a computational flow graph. It is a directed acyclic graph. There are no directed cycles. The nodes correspond to actual computation operations, and the edges correspond to flow of data, or tensors, if you will, which is, by the way, why TensorFlow is called TensorFlow. Okay, so that was the expression of an example as a computational flow graph. And automatic differentiation, we said, is a family of algorithms. First of all, it is not a single algorithm. There are two special cases of automatic differentiation, forward mode and reverse mode, but it is a family of algorithms, more than a family of size more than two, depending on the graph at hand, for implementing chain rule on a computational flow graph. There are many ways of implementing chain rule. In a chain structured graph, there are at least two canonical ways, but there are many ways of implementing chain rule. And how do we write that down as a program is what we will study today. That's what automatic differentiation is. And so let's keep these things separate. Automatic differentiation and Backprop, which is a special case of that, computes gradients. It is just an algorithm for computing gradients, for implementing chain rule. It does not tell you what to do with that gradient. You then have to follow an algorithm like gradient descent to take a step in the direction of the negative gradient. Okay, we introduced these two special cases in automatic differentiation. One was forward mode automatic differentiation, one was reverse mode automatic differentiation. We had zoomed into a node in our graph. That node performed a function g that transformed hl minus 1 to hl. And we had said that, somewhere down further into down this computational graph, an L is computed, somewhere up is an X, and we are interested in the partial of L with respect to X. In forward mode automatic differentiation, we operate in the same direction as the computation of L. So these arrows are telling us the order in which L is computed, right? Because HL has to be ready before HL can be computed. HL minus 1 has to be ready before HL can be computed. We operate in the same order. So we are following the same ordering of the edges. The input to forward mode automatic differentiation, it's a recursive or iterative algorithm where at each input to this algorithm is the partial of HL minus 1 with respect to X, the variable you want your gradients with respect to, and the output is the partial of HL with respect to X. And we had written them down as, following our chain rule notation, the layer Jacobian times this input. And in reverse mode automatic differentiation, our goals are still the same. The node that we're working on, G, is still the same. The only two salient differences is now we are operating in the opposite direction of the edges in the underlying computational flow graph. So the edges in the underlying computational flow graphs are going left to right. We are operating right to left in the opposite order. Left and right are, of course, relative terms. The formal term is we will reverse sort the topological ordering and proceed in that order. And the input is going to be the partial of L with respect to HL, and the output in reverse mode automatic differentiation is the partial of L with respect to HL minus 1. And of course, we will implement this by just chain rule computation at this node, which is, this is just an expression of chain rule. There's a matrix vector product here of L with respect to HL, HL with respect to HL minus 1. One of them is the layer Jacobian, one of them is the input to our algorithm. That vector matrix product will give us what we want. And so really the layer Jacobian is what we have to compute and implement, and this vector matrix product is the instantiation of chain rule at this node. Okay, so that was a quick refresher of where we were, slightly longer than I had intended, but it's important to get this rather than cover a lot of things that aren't clear. So any questions about this so far? Feel free to post it in the Q&A, but let's get started. So so what we will do is we will work through an example. We've given you the pieces of forward mode and reverse mode automatic differentiation, but let's actually work through this example to run through this piece to solidify our intuition. This is our same computational flow graph that we had said. F of x1, x2 is equal to sine of x1 plus x1 times x2. This is x1 is flowing on these edges, x2 is flowing on this edge. We called this thing W1, this thing is W2, W1 flows here, W2 flows here, and this intermediate variable is W3, which is the same as F. And we had said that our goal is the partial of F with respect to X. Let's say that's our goal, which notice is the same as the partial of F with respect to X1, the partial of F with respect to X2. So there are two terms here that we have to compute. Let's do forward mode automatic differentiation on this computational flow graph. How would we do it? Well, let's just focus on first of all, the computational nodes, right? These are the input nodes. These are special. We don't have to do anything here. So X1 and X2 we can ignore. Our formula says, or our algorithm says, we have to proceed in the order of these edges. In forward mode automatic differentiation, we have to operate in the order of these edges, and we will be propagating certain gradients. So let's take the first one. Let's, on this slide, compute partial of F with respect to X1. That's our goal. Let's compute that. And we have to start from the bottom. So on this edge, on the first edge, I have to send partial of X1 with respect to X1. Why? Because remember, that's how the input to forward mode automatic differentiation goes. We're working on this node. The sine of X1 is our node that we're doing this, and the input to our system is partial of the input with respect to X1, and the output that we'd like to compute is the partial of W1 with respect to X1, right? That's the output at this node. Let's just work through this. X1 with respect to X1, this is just 1. That part's easy. And what is the partial of W1 with respect to X1? Well, we know that W1 is equal to sine of X1. So the partial of W1 with respect to X1 is just cosine of X1. Right? So far, so good. That part's easy. On the other edge, this edge, we have to propagate partial of X2 with respect to X1, and that's just 0. Because X2 does not change because these are partial derivatives. X2 and X1 are by design, by definition of partial derivatives, X2 has no change with respect to X1. And along this edge, we have to compute the partial of W2 with respect to X1. which we've defined, W2 is equal to x1 times x2. So the partial of W2 with respect to x1 is just x2. And now when you get to this node, we have to define the partial of W3 with respect to x1, which, if we remember our chain rules correctly, is the partial of W3. So W3 we've already said is W1 plus W2. So it's just partial of W1 with respect to x1 and the partial of W2 with respect to x1. And these two terms, the cosine and the x2, just get added. So the thing that we're looking for, let me change font. Thing that we're looking for is cosine of x1 plus x2. Okay, this was not too terribly complicated. I mean, if I had to derive the partial of x with respect to x1, I could have just looked at this expression and derived the same thing. Like this derivation of cosine x1 plus x2 as this graph. I did not need this graph to do this. The reason why we are interested in writing down this graph is that we don't have to have a global understanding of the function. We just have to have a local understanding of cosine, of sine and product and summation to be able to implement, to be able to piece these together. Just like sine x1 plus x1, x2 can be implemented as first a sine, then a product, then a summation in this graph. Similarly, the cosine x1 and x2, the gradients can be implemented along this graph as well. Okay, so on this slide, we derived the partial of f with respect to x1. We followed simple rules on the edges. We can similarly derive an expression for the partial of f with respect to x2 by following the same set of rules. So we will go along these edges the same direction again. We know the partial of x1 with respect to x2. Why are we doing this? Because we know we want to operate at this node. The input to this node is x1, so we have to take the derivative of the input of this node with respect to whatever variable is our variable of interest. X2 is our variable of interest. We know this is going to be 0. Along this edge, the partial of x2 with respect to x2 is going to be 1. Along this edge, we have to get the partial of w1 with respect to x2, which we know this is the product, so this is just going to be x1. Right here, because the input to this sign is a 0 thing, once we implement chain rule at this node, we're going to multiply 0 by cosine, so the output is also going to be 0. So the partial of w1 with respect to x2 is also 0 just by following chain rule, which will multiply this by 0. And this summation, the partial of w3 with respect to x2, is just the sum of these two. So I'll get x1 here. And so this answer is x1. Notice again, I didn't need to follow this graph. The left half of this graph played no role because when I just stare at these expressions, I can just already see that if I take the partial of f with respect to x2, I know this term will not play any role, and I know that x1 times x2 is just going to give me x1 as that partial. I can see those things because I can see that expression, but it is important to step back and realize that our loss functions in future will be so complicated that you will not be able to see that answer. And so it is important to write down local operations that you can chain together. Okay, so I did 2 slides. In one, I derived partial of f with respect to x1. In another, I derived the partial of f with respect to x2. Turns out that you can actually combine both of those into a single slide and write down an expression that I've written here. I've written down a notation. So what I can do, remember, is we are looking for the partial of f with respect to x, and that is the partial of f with respect to x1 and the partial of f with respect to x2. And I can write a notation which is x1 dot, where x1 dot is the derivative or the partial of x1 with respect to some other variable a. I haven't told you what a is. It's just a temporary variable that I'm holding. And similarly, x2 dot is the partial of x2 with respect to this variable a. w1 dot is the partial of w1 with respect to A. If you're coming from a physics or mechanical engineering background, you're used to this notation. You're used to seeing, position and velocity and acceleration defined with the Newtonian notation of dots and double dots and so on. That's what's happening here. I'm just writing gradients or like partial derivatives with respect to a variable I haven't defined, A, which I will define in a second, as in the dot notation. So W2 dot is the partial of W2 with respect to A, and W3 dot is the partial of W3 with respect to A. So this is just how I've written things down. And turns out that if you just define this in this A notation, you can combine both of the previous two slides into an expression that is shown here. Cosine of x1 times x1 dot, and W2 dot is x1 dot x2 dot, x1 x2 dot. This is just chain rule at this node again, and W3 dot is W1 plus W2. None of these individual terms should be surprising. All that I've done is shoved those two slides as special cases into this common expression. And now all I have to do is I have to write for A in x1 comma x2, compute or evaluate. I should have written the for here. Evaluate this entire list. So just set A to x1 or x2, and it'll be clear what's happening here. When you set A to x1, this expression, these two expressions will be 1, and this expression will be 0, and then you'll forward prop or proceed in the order of directions of these expressions, and you will get the first term, the partial of f with respect to x1, by setting A to a particular value. And then you will set A to x2, and then this, let me change color. When you set A to x2, these two things will be 0, this will be 1, and then you will forward prop 0, 1 in this expression, and you will compute the second term of partial of f with respect to x2 by setting A equals x2. So far, so good. Any questions about this so far? That there is a for loop on the input variables, and I've written an expression down with respect to all that special iterator variable A that allows me to write this entire graph structure in terms of that special variable. Any questions on this so far? Because pop quizzes and questions are coming on the next slide. I will ask you what happens when I change X and what happens when I do other things. Any questions on this so far? Okay, if not, then here is, on the next slide, I'll ask you a question, but here is, for example, what forward mode automatic differentiation looks like on this thing. Notice that forward mode automatic differentiation is computing the partial of f with respect to x. We have written that down in terms of these special variables A. We have written forward mode automatic differentiation as a computational graph as well. And it will follow along these edges, and it will compute by setting A to x1 and x2. We will compute the partial of f with respect to x. Okay, so forward pass in a computational flow graph computes f. Forward mode automatic differentiation computes the partial of f with respect to x. They follow the same direction. Okay, pop quiz time. What happens to this computational graph if there is another input variable, x3? And by that, specifically, I mean that let's say I have a variable x3, and let's say my expression has become cosine of x3. So let's first take that question one step at a time. How do you think well, actually this will be hard, but if you can type out in the chat, how do you think the graph structure will change? And I realize that the simplest way is to draw it out, but if you can in words, try to describe how you think the graph structure will change as I add in x3, and in f I've added cosine of x3. Now I'll wait a couple of seconds. So what is happening is that we will add a new node, which is the cosine computation. X3 will be fed to it, and that will be fed to the plus. Oops, too far. x, and this will be fed to the plus sign. And then here, this will, let's call this W4 if we will, and there will be a W4 prime computation here. And so notice what needs to happen is now along these edges, there needs to be an x3 prime and a W4, not prime, x3 dot and W4 dot. That also needs to be propagated forward. So our computational flow graph changes, and our forward mode automatic differentiation also has to account for that. So that was structurally, that's the change. Computationally, the change is that you have to change your algorithm. For A in x1, x2, now it has to become x3. You have to loop over 3 input variables. And you have to, for example, when one of them, these two get set to 1, this gets set to 0, this gets set to 0. In another case, these two get set to 0, this gets set to 1, this gets set to 0. And in the third case, it's 0, 0, 1 that gets forward propagated. And so computationally, things get slower. You have a more sophisticated graph, of course, but you now need d+1 passes for d+1 variables. You added a new input variable. Therefore, because we've written everything down as, for loop in terms of input variables, we need one more pass in terms of input variables. Yep, and I'm seeing a couple of answers still coming in. Yeah, that part's correct. Okay, so everybody got that right. Let's ask another question. What happens if there's another output variable f2? And by that, what I mean is, let me just rename this to be f1, and let me rename f2 equals cosine of x2, for example. So if that is the case, I will now need to add a new output node. So there needs to be an intermediate node cosine. X2 goes here as well. So x2 is being sent there, and we now are computing two different things. There is a W4 being computed, and F2 is equal to W4, and so on, right? So there are two now output nodes. There's a W3 output node and a W4 output node, and so X2 bar and W4 bar are propagated along these things. The interesting thing in this case is that it is a more sophisticated graph, but you still only need D passes for D input variables. Your number of input variables has not increased because, apologies for the slide changing. Remember our thing says for A in X1, X2. Because the number of input variables has not changed, the number of output variables has changed, we still set these two to 1, these two to 0, and then opposite, these two to 0 and these two to 1, because the partial of x1 with respect to x2 and partial of x2 with respect to x1 and so on. And then forward prop to this, you will be able to compute all of f. F is now a vector with respect to x in the same two forward passes of this forward mode automatic differentiation graph. Does that make sense? That computationally things did not get, you did not have to add a new for loop, if you will. Yes, things got a little bit slower because yes, of course, you will have to compute sine to minus cosine and things like that on that branch, but you did not have to add a new for loop. Okay. Okay. So next, we will do exactly the same thing, but with reverse mode automatic differentiation. So we will take the exact same the function and the exact same computational flow graph, but we will do reverse mode automatic differentiation. In reverse mode automatic differentiation, we reverse the directionality of these edges, which corresponds to operating in the reverse of the topological order. So we will proceed in this order of propagation of information. Recall that, this is x1, this is w1, this is w2, this is x1 as well, this is x2, this is w3. We will start, so there, our goal, by the way, is still the partial of f with respect to x. That is still the goal. That has not changed. that is still equal to the partial of f with respect to x1 and the partial of f with respect to x2. That's still the case. The order in which we will operate is the opposite order, and we will introduce the intermediate variables that we will propagate. We will use a slightly different notation. So we will actually use the input here is the partial of f with respect to W3. That's what flows on this edge. And we will refer to it by W3 bar. And so instead of the dot notation, we have the bar notation here, which is equal to the partial of W3 with respect to itself, which is 1. So last class, somebody had asked, how do you start backprop if the thing at the end doesn't have any input? Well, the thing at the end is itself, and you take the partial with respect to itself, and that's why you always start the reverse mode automatic differentiation with 1, just like you start forward mode automatic differentiation with 1. The variable with respect to itself gives you 1. And what we will, let me just erase a little bit. Erase this edge and then draw it again on the outside so that it's cleaner. So we are operating this edge next. We will ask for W1 bar, which is partial of f with respect to W1. That's what we want. So this is just by definition, by convention. This is just how we're defining the bar notation. And notice that if we have to compute f with respect to W1, then we're just going to write down chain rule at this node. So it's f with respect to W3 times W3 with respect to W1, right? This is just chain rule. We know this object already. That's the input. That's W3 bar. And this is the object, which is the layer Jacobian, W3 with respect to W1. Notice that W3 is equal to W1 plus W2. And so the partial of W3 with respect to W1 is, someone tell me, what is the partial of W3 with respect to W1? It's not a trick question. It's a pretty easy question. 1. Thank you. Yes, it is indeed 1. And so you notice that the partial of f with respect to W1 is simply the partial of f with respect to W3, which also makes sense. It's just, on the way up, we were summing these things. On the way down, we are distributing these things. And so the same thing will happen here again. W2 bar is the partial of f with respect to W2, and we will find that it is equal to partial of f with respect to W3. And so a summation operation, by the way, on the way back in reverse mode, anytime you have a summation operation in a computational flow graph, in the reverse mode automatic differentiation, the summation operation is actually just distributing the gradients. It's the same gradient of f with respect to W3 that is being sent to this side of the branch and that side of the branch. Okay. And we will do one more. So we will actually go down this branch as well. We will have to compute x1 bar, which is the partial of f with respect to x1, which we will write down as the partial of f with respect to W1 and the partial of W1 with respect to x1. This again is input. We already know this from the above layer. This is W1 bar. We know this from the above layer, and W1 with respect to x1 we've just computed. This is our Jacobian. We know that W1 is equal to sine, and so this is cosine. Right? And we will do the same thing on this edge to compute x2 bar, on this edge to compute x1 bar as well. And this x1 bar will be different from this other x1 bar because the gradients on these edges are different. Okay, so simplifying some things and, excuse me, yeah. So simplifying some things and writing what I was scribbling down with equations, this is what it comes down to. You have this as the directionality of edges. You have a W3 bar that you set equal to 1, and then you get these recursive expressions. W2 bar is equal to W3 bar, W1 bar is equal to W3 bar, and X1 bar is W1 times W1 bar times cosine of X1. X1 bar is W2 bar times X2. X2 bar is W2 bar times X1. So you get these expressions on the way back. So simply set W3 to 1 and execute these expressions in the opposite order, and you will compute partial of f with respect to x. That's how, if you just run reverse mode automatic differentiation in the reverse order of the edges in the underlying computational flow graph, you will get this sort of an expression. You will compute partial of f with respect to x. Okay, and let's see. I will come back to this. There's actually the thing that I was going to mention is that in a reverse mode automatic differentiation, whenever in the forward mode, whenever in the forward pass or in the computation of the function, you have the same value being sent to two different places. So maybe there was an x1, there's a sine function here, and same sine of x1 is going here, and the same sine of x1 is going here. Anytime that happens, which we can call w1 and w1, anytime that happens, on the way back we sum up w1 bars coming from both of the two places. Why? Because this is just a instantiation of total derivatives, or the accumulation of partial derivatives along two different branches in chain rule. How do you compute both x bars? So I presume you were talking about this expression on this slide. How do you compute both x bars, or x1 bars and x2 bars? It's just chain rule applied again. So the x1 bar on this side we already derived. On this side, it's the same thing, that x2 bar is partial of f with respect to x2. We write that down as partial of f with respect to w2, and the partial of w2 with respect to x2. The partial of, let me actually clean this and do this well. If I'm going to answer this question, might as well do it well. So this is partial of f with respect to w2, and the partial of w2 with respect to x2. That's just chain rule. The partial of f with respect to w2 is w2 bar. That's why you get this expression right here. And the partial of w2 with respect to x2, well, we know that w2 is equal to x1 times x2. That's what this operation is doing. It's a product operation. So the partial of w2 with respect to x2 is just x1. That's just a layer Jacobian, and that's how you get this expression. And you do a similar calculation on this edge, and you get that expression as well. Okay, a lot of math, but let's do some more thinking, some more answering of these questions. So let's say what happens when there is another input variable x3. So similar questions. There is an input variable x3, and let's say that we were initially doing, this plus cosine of x3, same as what we had done initially. So in the computational flow graph, things follow like this. We do x3, and then we add it here, and w3 is equal to w1 plus w2 plus this one becomes a w4, right? So plus w4. So in the computational flow graph, an extra branch gets added. And therefore, in the reverse mode automatic differentiation, you follow the direction opposite to this. And so a w4 bar gets added and an x3 bar gets added. My question is this computationally slower in the big O notation sense? Do we get like if we have D input variables, do we have did our for loops increase? Do we have, so the space of answers is yes or no. Do we have another for loop as we did for the forward mode automatic differentiation? Yes or no? Yes, that is the right answer. That there is a more sophisticated graph, but there is still a single backward prop. The number of passes in the backward prop did not increase. I will ask the next question, which will actually change this calculus that this answer that you've given. Questions? So there's a question for me. what happens, similar to the last time, similar to forward mode automatic differentiation, what happens if there's another output variable f2? So if this is f1 and we define f2 to be cosine of x2, so we have not added another input variable, we've just added an output variable. And so in the computational flow graph, there is a cosine node that connects here, which then goes here. This is W4, which is the same as F2. And so in the reverse mode automatic differentiation, we have to have this edge, which is W4 bar, and an edge here, which is X2 bar. The thing is that now we have to define what W4 bar is. Is it the partial of F1 with respect to W4? Is it the partial of F2 with respect to W4? And just like we did in the forward mode automatic differentiation, there really is a for loop here for, let's say, A in F1, F2. There is some intermediate variable for A in F1, F2, you are running reverse mode automatic differentiation by saying partial of A, compute partial of A with respect to any particular variable, let's say W4. So W4 bar is this, is partial of A, W3 bar is the partial of A with respect to W3, and so on. So you run reverse mode automatic differentiation with respect to a particular output variable node, and then you have to write a for loop, and then you have to run it that many times. So there is a more sophisticated graph. There are C backward passes or props for C output variables, C output variables. So that's how things get more sophisticated. Okay, I want to take a second to cleanly delineate between three different kinds of computational flow graphs that you've seen already for this same example. The first is the computational flow graph corresponding to a forward pass in a neural network, which simply computes F. It operates in the same direction in the topological ordering of that graph, and it simply computes F. That's what we usually say when we mean, that's what we mean when we say forward pass in a neural network or in a computational flow graph. A forward pass computes F, which in your cases will be the loss. A forward mode automatic differentiation operates in the same direction of edges, but computes the partial of F with respect to X. So it computes the partial of all output variables with respect to all input variables, and you have to define what output and input variables are. A reverse mode automatic differentiation proceeds in the reverse order of the directions of edges of the underlying computational flow graph. It does not compute F, it computes the partial of F with respect to X. It's the same thing as what forward mode automatic differentiation computes. So the answers are not different, but the order of computation is different. But it's computing a different quantity as forward mode or as forward pass, because it's not computing F, it's just computing the partial of F with respect to X. Okay, some more questions. As soon as I give you two algorithms to do the same thing, it is very obvious to ask, when should I use one of these algorithms and when should I use the other algorithm? Why are you teaching me two algorithms? Why does one not suffice? And when is one good and when is one not good? And so the question I'm going to ask you is, which one do you think is faster to compute? In general, is forward mode automatic differentiation faster, or is backward mode automatic differentiation faster? Or is there not a general answer? So that's a question to you. Is forward mode automatic differentiation faster, backward mode, or it depends? Question. So let's hear the answers from people on chat. Which one is faster to compute? Forward mode, reverse mode, or it depends? So the way to understand this, the answer to this question. So the answer is depends. Is C greater than D or D greater than C? And the way to understand this is to think of the entire graph as a black box. You have an input variable X that lives in some RD. You have a computational graph or neural network or a differentiable program. It's the same thing. Everything is the same thing. You have some operation that takes in X and it produces, let's say, L. There are L loss functions. Maybe you're doing multi-target learning or like multitask learning, and so there are multiple loss functions. That's typically not the case. Typically, you just have one loss function. But let's think about this case for a second, right? What do we expect? What do we expect our object to be? The partial of L with respect to X is the Jacobian of your entire program. That's the Jacobian of the entire neural network. And this object is obviously a matrix. It's a matrix of size C cross T, because the ith row, jth column, as we've said, computes partial of Li with respect to Xj, right? What forward mode automatic differentiation, let me pick a color. What forward mode automatic differentiation does is it computes a column of this matrix at a time. So this is what forward mode automatic differentiation outputs in one pass. It tells you with respect to all losses how they are going to change with respect to Xj. So epsilon perturbations to Xj, how do all losses change? That's what it computes in one pass. And then therefore you write a for j in 1 through d, right? This is what forward mode automatic differentiation does. And let me change colors again. Reverse mode automatic differentiation computes one row of this Jacobian matrix at a time. It tells you, so this is reverse mode automatic differentiation output in one pass, and then you write a for I in 1 through C. So it tells you, reverse mode automatic differentiation picks a loss function and tells you how does that loss function change as you make epsilon perturbations to all one at a time, of course, with respect to all input variables. So computing one row of this matrix at a time or one column of this matrix at a time, how many passes you're going to need depends how many rows or columns you have. In most of deep learning, we only have one loss function. So the entire thing is just a long row vector, a long row vector. And so therefore, that is why we use reverse mode automatic differentiation, because in one pass, it can compute the entire row of this matrix. Forward mode automatic differentiation computes one column at a time. And so if the entire thing is just a flat one row vector, then you're just computing one scalar at a time. And what's happening is that there are intermediate computations that are not being reused. You compute a whole bunch of, in forward mode automatic differentiation, you compute things from bottom to top over and over again and keep throwing those intermediate computations away. In reverse mode automatic differentiation, you start from the top and you're going to the bottom and you are reusing the computations along the paths. And so the reason why you're able to reuse everything is because really there's one thing at the top and there are many things at the top and at the bottom. And that's, of course, an intuitive explanation of the whole thing. The mathematical explanation is right in front of you, is that we can reuse all the computations because what you were interested in computing is a row vector anyway. Okay, so hopefully that intuition is useful, that forward mode automatic differentiation computes the Jacobian of your program, of your entire computational graph, one column at a time, and reverse mode computes it one row at a time. Okay. I'll take a look at these questions in a couple of minutes. I just want to get through a couple of other questions. So we've answered this question, which one is faster? Now let's look at this question. Which one is more memory efficient? That is, which one uses less storage? So the question to you is it forward mode automatic differentiation that uses less storage, or backward mode automatic differentiation that uses less storage, or it depends again. Those are the three choices. Let's hear it. What do people think? The right answer here is forward mode automatic differentiation is more memory efficient. That is, requires less storage. And the reason why that is if you remember, there was a G function in forward mode automatic, or in both of them. You have an HL minus 1 and you have an HL. In forward mode automatic differentiation, you operate in this order. You are given the partial of L with respect to HL minus 1, and you compute the partial of L with respect to HL. This is what gets computed. Once you are done with this computation, you can throw HL minus 1 away. You do not need to store HL minus 1. You do not even need to store the partial of L with respect to HL minus 1. You can throw, once you are done with this computation of computing L with respect to HL, you can throw the inputs away. However, notice that in reverse mode automatic differentiation, we are at some G. G is some in-between neuron or node in this computational graph. It is neither the end nor the beginning. It's just some intermediate thing. There is HL minus 1 with respect to HL, and we are operating in the reverse order. We are given as an input the partial of L with respect to HL. Apologize, I've sort of messed up my thing. There's a typo here. Recompute is just, yeah, my argument stays the same, but I have a typo here with respect to X and the partial of L with respect to X. Okay, yeah, and on the reverse, you have to compute the partial of L with respect to HL minus 1. Now, the reason why reverse mode automatic differentiation is less memory efficient or requires more storage is, in order to compute this object, the L with respect to HL minus 1, you will need this as input, but you will also need HL minus 1 as input. Because in order to compute the Jacobian, a Jacobian is an expression, but then you evaluate that expression at certain point, and that point is this point. At HL minus 1 is when you evaluate this Jacobian. And so you will need to remember what were these activations coming in at which I'm evaluating my Jacobian. You cannot throw this away. You have to, therefore, in order to implement backprop, that is why when we implement backprop, we first do a forward prop to compute the softmax outputs and the losses, and then we start the backward prop from there, and we have to preserve the intermediate activations. If there's a fully connected layer, we have to remember what the activations were. We have to remember all the parameters were on the way forward. If there's a convolution, we have to remember convolutional feature maps. If there's an LSTM, we have to remember LSTM internal cell and memory and everything. It's because when we hit a neuron on the way back, we will need to know what the activation was in order to evaluate the Jacobian at that level, at that point. We cannot throw HL minus 1 away. And that right there is a problem. It is why implementing backprop, you often run out of memory on a GPU because you are storing all these activations. It is not the parameters of your neural network that are often so heavy. It is the activations that you're storing along the way that are heavy. If you have a batch of 100 examples, then all activations for all those 100 examples have to be stored till you can finish the backward pass. And that's what gets you into memory trouble. Okay, so forward mode is much more memory efficient, but it is typically in the kinds of problems we are doing not faster to compute. There are some narrow domain of problems where you have a small number of input variables and you have a large number of output variables. That happens, for example, when you want to do sensitivity analysis. As I change one pixel, how does my activation change in all these feature maps? Those sorts of sensitivity analysis is typically done with gradients, and there you want gradient of activation with respect to one particular pixel, and that is much faster to compute with forward mode automatic differentiation. But there are those cases are so rare that in most of the cases we use backward mode automatic differentiation in our things. Okay, so that's what we covered today. And here is finally the question that one of you asked. Can we see this neural network as a computational flow graph? Can we finally see this? I'd shown this last time as well, but this is what what a neural network or a multi-layer perceptron is as a computational flow graph. X is input, W1 is the parameters of the first layer. This layer is doing a matrix multiplication. If W is a matrix, this is a fully connected thing. There's also a bias embedded in there. So W times X plus B is happening due to F and a non-linearity. So you can do a max of W transpose X. So max of 0, comma W1 times X, where W1 already contains the bias. That's what F1 is. That's what H1 activation is. And then you just repeat that for different layers till the last layer is computing hinge loss or softmax cross entropy, which is a scalar. So this is what a neural network or a multi-layer perceptron or a fully connected neural network looks like as a computational flow graph. L is the as a thing. X, of course, is input, but we are interested in partial of L with respect to each of these W's. So we will need to run reverse mode automatic differentiation or backward prop all the way for each of these WIs, these matrices, because we will use that in gradient descent, right? So that's the in fact, you can actually write down reverse mode automatic differentiation or backprop in these neural networks as another computational graph. So there is del L, which starts at the size of 1. You compute the del WL and so on for each one of these objects. And computing the Jacobian of these things, these arrows are indicating that this information is used in this computation, is used in computing this thing. And that's why those arrows are present. And that's one of the major problems. Like if you have X living in some R D, you have H1 living in, let's say, some R of 256, then you have to keep these things around because you will need them on the way back. And if you have a batch size of B, then it's B times the 256, because that many examples you have to keep around. Okay, we will pick up, we're out of time, so we will pick up on how to chain these things into arbitrary DAGs next time, and how to go, we'll look at some examples also next time. I'm happy to answer questions that were unanswered so far and answer any other questions now, but people should feel free to log off. We are done with introducing any new content. So thank you.